let's have a look at some of these relationships that exist between the binomial coefficients. Remember, it all starts with the binomial theorem, which we've defined to be 1 plus x to the power of n, and I've written it in some notation there. So general term nck x to the k, starting from k equals 0 going up to n, and if we were to expand that out, we'd end up with nc0 plus nc1x, and so on up to ncn x to the power of n. So all these questions, basically we're starting with that idea. So if we had to find the value of k equals 1 to n of nck, so we start off with our binomial theorem. Now we have a look at what we're trying to prove, we have a look at what we've got. What do you notice is different straight away? Okay, yeah, so that one's got x to the power of k, this one doesn't have x to the power of k. How can we make it the same? We want that x to the power of k to look like it's disappeared. So if we let x equal 1, because 1 to the power of k is always equal to 1. But on the left-hand side, we'll have 1 plus 1 to the power of n. So it's close, but it's not quite what we want. Because what else is different, do we notice? Yeah, what we've got starts at 0. What we want starts at k equals 1. So if I withdraw from that sum the term where k is equal to 0, and if we were to sub 0 in, we'd just get nc0. Now my sum is going from 1 to n, everything's fine. All I've got to do is move the nc0 to the left-hand side, but we of course have another rule that says nc0, doesn't matter what n is, so we get our result, 2 to the power of n minus 1. Basically that's playing with the result of Pascal's triangle. Any row in Pascal's triangle will always add up to be 2 to the power of n. So some of them, but just the odd ones, just the odd ones. So again, we'll start with the binomial theorem. I just want the odd ones. Well, if I was to expand that whole thing out, there it is, but we've got both odd and even numbers. What we saw just before was that x equals 1, and those x's will go away, but that again has got all of them. How can I get rid of some? Via another substitution will be handy, but what's that substitution to be? Yeah, if we let negative 1 be x, or rather I probably should say let x be negative 1, then the signs are going to alternate. Now left hand side, 1 minus 1 is 0, but now I've got simultaneous equations. I want to be left with the, which ones was it? The odd ones. So if I was to, what we're going to do, add or subtract, we'd need to subtract, would we, get rid of all the even ones. And I get 2 to the power of n ends up being 2 lots of nc1, 2 lots of nc3, 2 lots of nc5, and so on and so on. Divide by 2, and we have our result. If I wanted all the even ones, then yeah, I'd do exactly the same thing, but just add the 2 together. And its total would end up being exactly the same, 2 to the power of n minus 1 as well. K times nck. There's our binomial theorem. Have a look at what we got. Have a look at what we want. How do they differ? It's more than just the x going away this time. What mathematical operation do we know that will put k in front of the term? See it? Calculus. So if I differentiate both sides, then I get k nck x to the k minus 1. But now I can do that substitution again. Let x equal 1. And how close are we? Again, they wanted from 1 to n. We've got 0 to n. So pull out the 0. Well, actually, that term turned out to be 0 anyway. But that's all right. So we now have our relationship. N times 2 to the power of n minus 1. We know that 1 plus x to the power of n times 1 plus x to the power of n is essentially the same as 1 plus x to the power of 2n. Add the powers. So using that, we have to show this lovely result. It all starts with the binomial theorem. So there's 1 plus x to the power of n, which if I was to expand out, would be that. We want to find the coefficient of x to the power of n. So start with the left-hand side. So I've got this 1 plus x to the power of n, and I'm multiplying it by itself. I just want the terms that will produce x to the power of n. So the nc0 must be times the ncn x to the n. the NC1 must be times the NCn minus 1 x to the n minus 1. The NC2 x squared times the NCn minus 2, and so on and so on and so on. We get the whole expression. Okay, so the coefficient, I'm not interested in the x to the power of n, it's just the coefficient I'm interested in. We get NC0, NCn plus NC1, NCn minus 1, and so on. Not quite what we want, so now we have to use another one of Pascal's triangles identities. Remember, it's symmetric. So NCk is the same as NCn minus k. So I could rewrite that, instead of writing NC0 times NCn, well that's NCn is the same as NC0. So we've got NC0 squared. Then in the next term, well NCn minus 1, that's the same as NC1. We get NC1 squared. And we can do that for each of the terms. I've got the left-hand side of what we're trying to prove. Okay, now the right-hand side. The coefficient of x to the power of n in 1 plus x to the power of 2n. Well, in all that expansion, somewhere in the middle, there'd be 2NCn x to the n. There's only going to be one term in that expansion that's x to the power of n. So that's what I'm looking for. Well, they are the same expression, so therefore those coefficients have got to be the same. Still not quite what we're trying to prove. Left-hand side's okay. Right-hand side, we've got to go to our definition. So 2n factorial over n factorial, which is n factorial squared. And there's our proof. Oop.